Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Machine Learning Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You recently trained an XGBoost model on tabular data. You plan to expose the model for internal use as an HTTP microservice. After deployment, you expect a small number of incoming requests. You want to productionize the model with the least amount of effort and latency. What should you do? The options are: Option A, deploy the model to BigQuery ML by using create model with the boosted_tree_aggressor statement, and invoke the BigQuery API from the microservice. Option B, build a Flask-based app. Package the app in a custom container on Vertex AI, and deploy it to Vertex AI endpoints. Option C, build a Flask-based app. Package the app in a Docker image, and deploy it to Google Kubernetes Engine in autopilot mode. Option D, use a pre-built XGBoost Vertex container to create a model, and deploy it to Vertex AI endpoints.
To arrive at the correct answer, we focus on the keywords: trained in XGBoost model, HTTP microservice, least amount of effort and latency.
The correct answer is option D, use a pre-built XGBoost Vertex container to create a model, and deploy it to Vertex AI endpoints.
Why is this correct? D. Vertex AI endpoints provides a fully managed solution with pre-built containers specifically for XGBoost, which minimizes deployment effort and offers the required low latency for HTTP microservice requests. Why are the others incorrect? A. BigQuery ML is optimized for batch analytical workloads rather than low latency serving for an HTTP microservice, and retraining the model inside BigQuery adds unnecessary effort. B. Building a custom Flask application and managing a custom container requires significantly more development and maintenance effort compared to using a readily available pre-built container. C. Deploying and maintaining a custom Flask application on Google Kubernetes Engine, even in autopilot mode, involves much higher operational effort than using a managed service like Vertex AI.
You need to use TensorFlow to train an image classification model. Your dataset is located in a cloud storage directory and contains millions of labeled images. Before training the model, you need to prepare the data. You want the data pre-processing and model training workflow to be as efficient, scalable, and low maintenance as possible. What should you do? The options are: Option A, 1. Create a Dataflow job that creates sharded TF record files in a cloud storage directory. Point 2. Reference tf.data.tf record dataset in the training script. Point 3. Train the model by using Vertex AI training with a V100 GPU. Option B, 1. Create a Dataflow job that moves the images into multiple cloud storage directories, where each directory is named according to the corresponding label. 2. Reference tfds.folder_dataset, image folder in the training script. Point 3. Train the model by using Vertex AI training with a V100 GPU. Option C, 1. Create a Jupyter notebook that uses an NT standard 64 V100 GPU Vertex AI workbench instance. Point 2. Write a Python script that creates sharded TF record files in a directory inside the instance. Point 3. Reference tf.data.tf record dataset in the training script. Point 4. Train the model by using the workbench instance. And the remaining options are: Option D, 1. Create a Jupyter notebook that uses an N1 standard 64 V100 GPU Vertex AI workbench instance. Point 2. Write a Python script that copies the images into multiple cloud storage directories, where each directory is named according to the corresponding label. Point 3. Reference tfds.folder_dataset.image folder in the training script. Point 4. Train the model by using the workbench instance.
To arrive at the correct answer, we focus on the keywords TensorFlow, millions of labeled images, efficient, scalable, and low maintenance as possible.
The correct answer is option A, 1. Create a Dataflow job that creates sharded TF record files in a cloud storage directory. Point 2. Reference tf.data.tf record dataset in the training script. Point 3. Train the model by using Vertex AI training with a V100 GPU. Review the options on screen.
Why is this correct? A. Dataflow efficiently scales to pre-process millions of images into sharded TF record files, the optimal format for TensorFlow. Vertex AI training provides a highly scalable, low-maintenance managed environment for training. Why are the others incorrect? B. While Vertex AI training is suitable, tfds.folder_dataset is significantly less efficient than TF record dataset for millions of images, as reading individual image files directly limits training throughput. C. Pre-processing inside a single workbench instance does not scale for millions of images compared to Dataflow. Additionally, training on a workbench instance is not as low maintenance or scalable as Vertex AI training. D. A single workbench instance limits scalability for both pre-processing and training. Copying millions of individual images and using an image folder dataset is highly inefficient compared to Dataflow and TF records.
You recently deployed a model to a Vertex AI endpoint. Your data drifts frequently, so you have enabled request-response logging and created a Vertex AI model monitoring job. You have observed that your model is receiving higher traffic than expected. You need to reduce the model monitoring cost while continuing to quickly detect drift. What should you do? The options are: Option A, replace the monitoring job with a Dataflow pipeline that uses TensorFlow Data Validation, TFDV. Option B, replace the monitoring job with a custom SQL script to calculate statistics on the features and predictions in BigQuery. Option C, decrease the sample_rate parameter in the random sample config of the monitoring job. Option D, increase the monitor_interval parameter in the schedule config of the monitoring job.
To arrive at the correct answer, we focus on the keywords Vertex AI model monitoring job, higher traffic than expected, reduce the model monitoring cost, quickly detect drift.
The correct answer is option C, decrease the sample_rate parameter in the random sample config of the monitoring job.
Why is this correct? C. Decreasing the sample_rate in random sample config reduces the volume of data processed for monitoring, directly lowering costs while still maintaining a representative sample to detect drift quickly in high-traffic scenarios. Why are the others incorrect? A. Replacing the job with a Dataflow pipeline using TFDV adds development overhead and maintenance complexity compared to natively configuring the existing managed model monitoring service. B. A custom SQL script introduces unnecessary engineering effort and operational overhead when Vertex AI already provides built-in managed model monitoring features for drift detection. D. Increasing the monitor_interval parameter delays the detection of data drift, which contradicts the explicit requirement to quickly detect drift.
You work for a retail company. You have been asked to develop a model to predict whether a customer will purchase a product on a given day. Your team has processed the company's sales data and created a table with the following rows: customer_ID, product_ID, date, days_since_last_purchase, measured in days, average_purchase_frequency, measured in 1/days, purchase, binary class. If customer purchased product on the date, you need to interpret your model's results for each individual prediction. What should you do? The options are: Option A, create a BigQuery table. Use BigQuery ML to build a boosted tree classifier. Inspect the partition rules of the trees to understand how each prediction flows through the trees. Option B, create a Vertex AI tabular dataset. Train an AutoML model to predict customer purchases. Deploy the model to a Vertex AI endpoint and enable feature attributions. Use the explain method to get feature attribution values for each individual prediction. Option C, create a BigQuery table. Use BigQuery ML to build a logistic regression classification model. Use the values of the coefficients of the model to interpret the feature importance, with higher values corresponding to more importance. Option D. Create a Vertex AI tabular dataset. Train an AutoML model to predict customer purchases. Deploy the model to a Vertex AI endpoint. At each prediction, enable L1 regularization to detect non-informative features.
To arrive at the correct answer, we focus on the keywords, predict whether a customer will purchase a product, interpret your model's results for each individual prediction.
The correct answer is option B, create a Vertex AI tabular dataset. Train an AutoML model to predict customer purchases. Deploy the model to a Vertex AI endpoint and enable feature attributions. Use the explain method to get feature attribution values for each individual prediction.
Why is this correct? The Vertex AI feature attributions, explainable AI, is designed specifically for providing local explanations. It calculates how much each feature contributed to each individual prediction when using models like AutoML Tabular. Why are the others incorrect? A. Inspecting the partition rules of boosted trees in BigQuery ML is tedious and highly impractical for interpreting each individual prediction, especially for large and complex tree ensembles. C. Logistic regression coefficients provide global feature importance across the entire dataset, but they do not provide local, instance-level feature attributions for each individual prediction. D. L1 regularization is a training technique used for global feature selection by adding a sparsity penalty. It does not provide feature attributions or interpretations for individual predictions at inference time.
You have built a custom model that performs several memory-intensive pre-processing tasks before it makes a prediction. You deployed the model to a Vertex AI endpoint and validated that results were received in a reasonable amount of time. After routing user traffic to the endpoint, you discover that the endpoint does not autoscale as expected when receiving multiple requests. What should you do? The options are: Option A, use a machine type with more memory. Option B, decrease the number of workers per machine. Option C, increase the CPU utilization target in the autoscaling configurations. Option D, decrease the CPU utilization target in the autoscaling configurations.
To arrive at the correct answer, we focus on the keywords, memory-intensive preprocessing tasks, endpoint does not autoscale as expected.
The correct answer is option D, decrease the CPU utilization target in the autoscaling configurations.
Why is this correct? D. Memory-intensive workloads often reach their limits without generating high CPU usage. Decreasing the CPU utilization target ensures the autoscaler triggers at lower CPU levels, allowing the endpoint to scale out correctly under load. Why are the others incorrect? A. Upgrading the machine type is vertical scaling and does not address the underlying configuration issue preventing the horizontal autoscaler from triggering. B. Decreasing the number of workers might help prevent memory exhaustion per instance, but it does not resolve why the autoscaler fails to trigger. C. Increasing the CPU utilization target would require even higher CPU usage to trigger autoscaling, which would exacerbate the problem for a memory-intensive workload.
You are creating a model training pipeline to predict sentiment scores from text-based product reviews. You want to have control over how the model parameters are tuned, and you will deploy the model to an endpoint after it has been trained. You will use Vertex AI pipelines to run the pipeline. You need to decide which Google Cloud Pipeline components to use. What components should you choose? The options are: Option A, Tabular Dataset Create Op, Custom Training Job Op, and Endpoint Create Op. Option B, Text Dataset Create Op, AutoML Text Training Op, and Endpoint Create Op. Option C, Tabular Dataset Create Op, AutoML Text Training Op, and Model Deploy Op. Option D, Text Dataset Create Op, Custom Training Job Op, and Model Deploy Op.
To arrive at the correct answer, we focus on the keywords, text-based product reviews, control over how the model parameters are tuned, deploy the model to an endpoint.
The correct answer is option D, text dataset create op, custom training job op, and model deploy op.
Why is this correct? D. Text dataset create op is required for text data. Custom training job op provides full control over hyperparameter tuning, unlike AutoML. Model deploy op correctly deploys the trained model to a Vertex AI endpoint. Why are the others incorrect? A. Tabular dataset create op is incorrect because the data is text, not tabular. Additionally, endpoint create op only creates the endpoint resource but does not deploy the trained model to it. Model deploy op is needed for deployment. The AutoML text training op is incorrect because it does not allow fine-grained control over model parameter tuning. Furthermore, endpoint create op only creates an endpoint resource without deploying the model to it. C. Tabular dataset create op is incorrect because the dataset consists of text reviews, not tabular data. AutoML text training op is also incorrect as it does not provide the required control over parameter tuning.
You need to deploy a scikit-lean classification model to production. The model must be able to serve requests 24/7, and you expect millions of requests per second to the production application from 8 a.m. to 7 p.m. You need to minimize the cost of deployment. What should you do? The options are, option A, deploy an online Vertex AI prediction endpoint. Set the max replica count to 1. Option B, deploy an online Vertex AI prediction endpoint. Set the max replica count to 100. Option C, deploy an online Vertex AI prediction endpoint with 1 GPU per replica. Set the max replica count to 1. Option D, deploy an online Vertex AI prediction endpoint with 1 GPU per replica. Set the max replica count to 100.
To arrive at the correct answer, we focus on the keywords, scikit-lean classification model, serve requests 24/7, millions of requests per second, minimize the cost of deployment.
The correct answer is option B, deploy an online Vertex AI prediction endpoint. Set the max replica count to 100.
Why is this correct? B. A high max replica count handles peak load by scaling up, and minimizes cost by scaling down off-peak. CPUs are sufficient and cost-effective for scikit-learn models. Why are the others incorrect? A. A max replica count of 1 is insufficient to handle millions of requests per second, leading to dropped requests. C. A single replica cannot handle the peak load. Also, GPUs are unnecessary for scikit-learn models and violate the cost minimization requirement. D. Scikit-learn models run efficiently on CPUs. Using GPUs significantly increases deployment costs unnecessarily, violating the requirement to minimize cost.
You are developing a classification model to support predictions for your company's various products. The dataset you were given for model development has class imbalance. You need to minimize false positives and false negatives. What evaluation metric should you use to properly train the model? The options are, option A, F1 score. Option B, recall. Option C, accuracy. Option D, precision.
To arrive at the correct answer, we focus on the keywords, class imbalance, minimize false positives and false negatives, evaluation metric.
The correct answer is option A, F1 score.
Why is this correct? A. F1 score is the harmonic mean of precision and recall. It balances both false positives and false negatives, making it the ideal metric for datasets with class imbalance. Why are the others incorrect? B. Recall focuses solely on minimizing false negatives and does not account for false positives, making it insufficient for this goal. C. Accuracy is heavily skewed by the majority class in imbalanced datasets, leading to misleading results when evaluating model performance. D. Precision focuses solely on minimizing false positives and does not account for false negatives, making it insufficient for this goal.
You work for a bank and are building a random forest model for fraud detection. You have a dataset that includes transactions, of which 1% are identified as fraudulent. Which data transformation strategy would likely improve the performance of your classifier? The options are: Option A, write your data in TF records. Option B, Z-normalize all the numeric features. Option C, oversample the fraudulent transaction 10 times. Option D, use one-hot encoding on all categorical features.
To arrive at the correct answer, we focus on the keywords: random forest model, 1% are identified as fraudulent, data transformation strategy.
The correct answer is option C, oversample the fraudulent transaction 10 times.
Why is this correct? C. Oversampling the minority class, fraudulent transactions, addresses the severe class imbalance, 1%, allowing the model to learn the minority class patterns effectively instead of being biased towards the majority class. Why are the others incorrect? A. TF records is a data format for efficient reading in TensorFlow, not a data transformation strategy that improves a model's predictive performance on imbalanced datasets. B. Random forests are tree-based models and are inherently invariant to monotonic transformations of individual features. Z-normalization typically does not improve their performance. D. While one-hot encoding is useful for categorical features, it does not directly address the primary issue of severe class imbalance, which is the main obstacle in this scenario.